Hi everyone. So before we get going on this presentation, let me take a few moments just to give a little introduction of myself and to also say a few thank yous to the people who have invited me here today. My name is Josh Racette, and I am currently a PhD candidate in the Department of Engineering Physics at McMaster University in Hamilton, Ontario, Canada. My supervisor at the moment is Dr. Shinny Nagasaki, and he is currently actually the radioactive waste management research chair of Canada. So I graduated from my undergraduate engineering physics degree in 2017, and then in September of that same year, I joined Dr. Nagasaki's group and began this journey through my grad school. Before we continue any further, a couple quick thank yous. I want to say thank you to Maria Polizanen. She was the one that reached out and offered this opportunity to me to present for you all here. And in addition to Maria, the university deserves a thank you. It's actually a wonderful way to learn about engineering in general, engineering faculties, and engineering all over the world. And finally, I want to say thank you to all of you. So thank you so much for taking the time out of your day to watch this presentation, and I hope you actually do enjoy this presentation. So without further delay, let's just get this presentation underway. So what we're going to talk about mainly is the focus of engineering physics at McMaster University. And what I would like to do is share what kind of an education our undergraduate students can obtain and which can be supplemented while they are here at McMaster. Then I would actually like to show off the faculty in my department and highlight what some of the research is that this department is capable of. Next is if and when our students decide that graduate school just is not for them, they are typically very capable of getting a job after they've graduated, and we're going to touch up on that. And then the final topic of our little presentation today is actually my personal research here at McMaster. But since that's near the end of the presentation, if you are more inclined to, you can just sit back and enjoy listening to me talk, or if you want to listen and learn, by all means, feel free. So, what is engineering physics at McMaster University? Well, engineering physics at McMaster is actually an extremely diverse faculty that completely allows for the students themselves to dictate their own education in terms of the classes that they select, and which, given the diversity of our faculty, it's a wonderful opportunity to actually become a unique and learned individual. At McMaster University right now, students will all take a general first year course, and then upon entering their second year, what they do is they specialize into their specific streams within the overall engineering department. So some other faculties at McMaster that we do have are mechanical, civil, electrical and computer engineering, mechatronics, and there's actually even more of them. But because I'm a physical engineer, and this is the topic of this presentation, let's focus on what engineering physics at. So within our department, we actually have 6 streams that students can choose from, either taking all the courses in one stream, or they can diversify their mixture and take from all of them, or from 2 or 3, whatever. The 6 streams that our department typically focuses on is nuclear systems technology, photonics engineering, nano and microtechnology devices, smart systems technology, biomedical engineering, and then an interdisciplinary field, and that's when you take courses from all of them. So I have to say though, when I was graduating in 2017, the definition of the streams were only the nuclear, photonics, and the nano and microtechnology. So within the 3 years of me being in grad school, this department has just grown exponentially, I almost feel. So not just that, the department actually also teaches a wide range of courses. I mean, we have 6 streams, or it actually allows for courses to be taken from other faculties. And I personally think that's remarkable, as it shows the breadth of knowledge that an engineering physicist can have. So to give you the courses that are possible to be taken as an undergraduate student, and they're classically associated with a single stream, this slide actually shows us what the undergraduate courses are taught by the department within the nuclear stream, because that's what I took. I did nuclear engineering, so these are the courses I took. So I want to highlight something though. I want you to keep in mind the variety of the scientific education that's being taught by one department, all from faculty members in one department. And I think that's phenomenal, actually, because that's a very detailed scientific variety of courses right there. So also included on the slide are some of the technical electives that I've taken, which actually allow me to really fine-tune the physical engineering education that I wanted. So I personally have taken fluid mechanic courses from the mechanical engineering department. I've taken radiation safety courses from medical physics, and I've taken actually a theoretical quantum chemistry course taught by chemistry completely outside of engineering, which is pretty cool, actually. Forward and say, I actually want to say I think it's simple to say what the focus of a civil engineering program is or should be, and that's not a bad thing by any means. But what I mean by that is you should be able to get the information about the person who says they go to school for civil engineering and what kind of a career they should have and how capable they should be of completing it to make clients happy. I think if you say you went to civil engineer or you were a civil engineer, people can put that puzzle together for you. But there's a question, what is engineering physics? And this is actually still one of the most asked and improperly answered questions by students in our department themselves. So we're going to do it two ways. I actually have I want to present what I believe the focus of engineering physics is at McMaster and in the world, and as I've grown in my own personal life and learning my own role in the universe. And I think that the focus is to teach and develop students into thinkers and doers that have some of the highest expectations of any engineering department. I think it's absolutely remarkable how much we can do and how much we know. In addition, though, on our website, there's actually an answer to this question. What is EngPhys? What is? Provide you the answer here that is on our website. So, engineering physics is actually an interdisciplinary field of study where new and advanced materials, devices, and systems are engineered based on our fundamental understanding of physics. And that's crucial because we're not using engineering. We're not using what has happened before with engineering. It's physics. This is fundamental physics. Engineering, our faculty and students are involved in pushing the envelope of new technologies. Engineering physics combines physics and engineering to solve the most challenging problems in society today. Some people would call it applied physics, some people would call it the engineering sciences, and I actually want to say that I think it's more applied than physics, and it's the broadest discipline in engineering. Engineering physics students need to have a knowledge of mechanics, electricity and magnetism, the application of that to electronic devices and circuitry. They need to know computation and simulation capacity and how to do that. They need to know thermodynamics, properties of materials, and quantum mechanics. Look at all those different departments that one single individual is able to learn. So as you can see, there really is. This is the program that provides a breadth of knowledge that you cannot be obtained in any other program. And this is the knowledge that is required to actually drive technology forward and make a real impact on society today. I want to say that I really do think that this is an important answer. And why? Is because being able to naturally exist in so many different fields of the world shows a true capability to lead and work. And as people will gravitate more towards individuals who show this capacity to work, to achieve goals, overcome difficult challenges, and even create things, I think people will naturally find you as a leader. And then I also want to say, I think this is the only faculty that accepts the laws of physics as laws, and but also as the guideline that we can straddle, and that's how we get these exciting breakthroughs. I also want to say, if you're interested, though, in seeing any of the other courses that we teach, I only show the nuclear ones, go to our website at eng.mcmaster.ca/engphys. click on the research section there, and then click on areas of specialization, and then you can just go through it and spend some time reading. So now that we finished up what the kind of education our students can have is, what are the primary areas of research at McMaster University in our department? I think that's crucial. What does the faculty actually do here? So the diversity in research is remarkable to me. And I said that about like learning, but no, the research is remarkable. And if you're actually a student entering second year, you can join any of these research groups as a summer undergraduate student. So I previously said that there were 6 streams, but I'm only going to care about the 3 because that's how I feel. It is more for me because that's what they were when I graduated. So moving into our faculty members, the first one we're going to talk about is Dr. Jonathan Bradley, and he actually works with silicon-based photonic devices to revolutionize next-generation electronic devices. Here's actually, if you don't know in academia, it's very impressive to be offered the journal cover, and it's all color, looks fancy, but that's his research on the front of Laser and Photonics Reviews. Very, very fun. The next person on this page is Dr. Harold Haugen. He's actually a wonderful person to talk to, but his research deals with femtosecond laser ablation and micro machining. So what this is where you take ultra-fast laser pulses and you can actually decrease the amount of energy you're depositing into the surrounding material, which decreases the deformations for micro machining purposes. Very, very cool. Our current department chair is Professor Raphael Kleiman, and he's actually an active solar cell researcher. And just, I think 4 years ago, he received a massive solar cell grant, multi-millions. Very, very cool. Next up on this page here is Dr. Ray Lapierre, and he was the chair when I was an undergraduate student, but what he does is actually revolutionizing and pushing the boundaries of semiconductor research by using nanowires. So again, here's another cover shot. We have 2 ENCHPHS props who have cover shots. That's awesome. But there's also a small little picture of the nanowires themselves, and if you are interested, by all means, just research silicon nanowires. They're very, very interesting. Our first nuclear professor is Dr. John Luxat, who is up here in the top row. And Dr. Luxat's actually the current research chair in nuclear safety analysis for Canada. And I'm actually taking a class right now taught by him, which is nuclear safety analysis. How cool is that? And then we have a little picture up here. Since I'm nuclear, I'm just going to take a little second. But you can really see the difference in a nuclear fuel rod between the amount of energy that's deposited between being fine and being catastrophic. And then also on this page is actually one of the more younger professors in our department, but still actually has extremely exciting research, and that's Dr. Matthew Minnick. So he's focusing on microelectronic machine systems, which are MEMS devices, which you probably find more in mechatronics engineering or mechanical engineering. But what he does is he's actually designing tiny flying robots to mimic behaviors of real insects. So he's using these curved cantilevers, and when the curvature changes fast, you can think of it as a beating wing. Just very, very cool stuff. And then next group of professors, one of my supervisor is Dr. Shinny Nagasaki here. I won't spend too much time on him because I'm going to talk about my research moving forward, but he's very active in trying to ensure that Canada has their plan in place to dispose of 60 years of nuclear fuel. But he's also very active in developing engineering ethics with his students and understanding how students have their ethics form as they're growing into an engineer. And then the first professor, who is a female, I want to talk about, and that's Dr. Leila Soleimani. And she's actually kind of becoming a celebrity in the scientific community all by herself. And this is one of the coolest things, I think. She recently helped create a handheld detector that can pick up cancer biodetectors long before there's actually a possibility of it being too late for the person. And that is amazing to me. Just remarkable research. And then I'm gonna, here's a little picture that I want to include because it's Dr. Soleimani with her family. And if there's any women who are watching this presentation, I just want to say, if you've considered your career and your familial life clashing in the future, I hope you get to look at someone like Dr. Soleimani who's able to provide proof that women researchers can literally do everything male researchers can, make a name for themselves as a celebrity, and then still be a time to be a wonderful mother, because I can guarantee you that's something I cannot do. And then the next and the final faculty member I'm just going to focus on is Dr. Ace Tarak, and she is actually working with organic photovoltaics. So when you apply a stimulation of some kind by an external field or whatever it has to be, the natural laws of thermodynamics and entropy govern how that photovoltaic will change. And if you understand the situation that you're in well enough that you can take an organic photovoltaic and then go, I need to do this to it, you are physically engineering for your benefit. And I hope you could just see sort of what like the researches our department can do, because it's so broad, it's so wide. But obviously, not every student feels inclined to attend graduate school or further their quest for knowledge or another piece of paper. In fact, a lot of our students actually graduate and find wonderful jobs all over Canada or the country, all over Canada or the world. I hope you know that there's just a lot in this department. So, before we continue too far, I just want to quickly add in that we can supplement engineering physics education with these research institutes and centers that we have access to. So, me personally, I like the Canadian Centre for Electron Microscopy and the McMaster Nuclear Reactor. So, here's a little picture of me in front of the McMaster Nuclear Reactor core, and that little blue light is a cause of radiation. Some facilities that students can have access to, taking in courses, whatever so may be. In fourth year, students can build a silicon biomedical sensor, like an ion-sensitive field effect transistor. This is the one that I made that I was able to frame and now have it on my mantle. It's pretty cool. We have Dr. Fang, who's a researcher in our department, who's involved with smart systems technology. And what he's actually doing is finding a way to develop a home that can assist senior living without having anyone help them. The home is the assistant, is the assistant. Very, very cool. And then nuclear safety labs. It's important to teach nuclear engineers how to be safe with nuclear reactors. And I'm actually I highlighted this one just because I'm the TA for this course. And in the past, I've TA'd the third year intro to nuclear engineering courses as well. So there's just really so much different ways that our students can learn. That's not just in a classroom. Now we're going off into the labor market. So how are engineering physics graduates hired and then integrated into that labor market? And is there any indication of what companies can hire us? So before I mention what companies can hire, I think it helps knowing exactly how our students go about finding jobs. Keep in mind, I came to grad school. I was not ready for the adult job yet. So our department and the whole faculty actually has numerous job fairs throughout the year to promote companies, have companies come in, meet our students, but to also allow companies to recruit them, engage with them, and then actually just actively get involved. So the company almost becomes a name that we can associate while we're as a student. So whether it happens to be online applications or face-to-face meetings, many of our students actually find themselves fully capable of securing employment that's actually waiting for them upon graduation. So they graduate in April and there's the job waiting for them in May. I know some students who have taken a summer off, but they actually have honestly, they don't seem to have an issue being hired in the fall when they come back. And then I'm going to leave this slide up for a little bit so you can have some time to read some of the companies that hire EngPhys students. But I actually personally had a job interview when I was in my master's, and during the interview, they told me that I would be better suited for the job above the job I applied for, and they offered me the better job, but I declined it to pursue this PhD instead. So I really just want to say that it seems like our students are fully capable of being easily hired, given the knowledge that we have in our background and our capabilities. So when students go into the job market, they're an engineer in training in Canada, and that's until they get enough supervisory experience from a professional engineer. But I just honestly believe that even though there is this requirement, a lot of our graduates have no problem getting jobs. So as you can see, there's a ton of companies on this one image, like for nuclear engineering, for photonics, and there's some companies that even share different streams. So I really just hope that this kind of thing shows the diversity in our department from a researcher's perspective, from a learning perspective, and really shows you what kind of an education you can get from this kind of department. I have to say though, these are only Canadian companies as far as I know. EngPhys students don't need to stay in Canada. We actually have the potential to travel the world and work all over the world. One of my co-workers was able to spend a summer at the Japanese Atomic Energy Agency in Japan. And this is actually a little blurb from a time from my first summer. I actually was able to secure a co-op as a researcher at Lawrence Berkeley National Labs in Berkeley, California, where I started a collaboration, which I'll talk about in my research, but the collaboration is still going well. And I just think I think this is a great way to show that physical engineers don't need to be constrained to one location in the planet. We really have the ability to go all over the planet, because we can physically change the world when we get there. I'm going to leave this slide up for a little bit so you can have some time to read some of the companies that hire EngPhys students. But I actually personally had a job interview when I was in my master's, and during the interview, they told me that I would be better suited for the job above the job I applied for, and they offered me the better job, but I declined it to pursue this PhD instead. So I really just want to say that it seems like obviously getting hired by somebody is one way of making a life, a living. There's also another way, and that's when you do it. Do engineers start their own startups? And obviously, yes, engineers always do start their startups. I can't give a list like that last one that was up, but I know that there are numerous companies that have been created or that are running that their whole role is to supply a very niche but a very valuable resource or technology, and that's a really unique thing for an engineering physics startup, I find. So the reason why I think that is, though, is because I believe physical engineers actually have a capacity to understand the world uniquely macroscopically and microscopically, and then meet them in the middle. And because of that, we actually have the ability to lead to innovative solutions that we can remarkably profit from. So I want to highlight, actually, there was a Global Entrepreneurship Week a month ago, and 6 McMaster engineering startups were chosen to be represented by it, and they're all thriving successfully. So 6 startups already from our alumni or our current students, and then this one's actually even more personal to me. I think it's very crazy, actually. Here we have on the right-hand side some EngPhys students who made a guitar tuning robot for their 4th year capstone project, and they're actually able to secure a position on the Dragon's Den TV show and try and sell that. And they were in 4th year, and I've TA'd them. That's pretty cool. So, like I said though, or like I was about to say, I really think that physical engineers can see the gap in the market. And then when they see that gap, they have the technical and economic know-how to fill it, which is a successful startup for a company run by an engineer. And I think this is, you're probably going to like this, but I've actually, I wouldn't say it's a startup yet, but October was the 6-month anniversary of my company. And basically, I've always been a fan of plants. I like growing plants. I like having house plants, especially cacti. And over the years, I found this one cactus is hard to get, it's just hard to get. But then I found I could finally get one, and I just fell in love with them. I just think they're adorable plants with just the way they look, with the wool and that flower, just phenomenal. But they're actually some of the slowest growing plants in nature. And for me to make a profit, though, what I think I need to do is physically engineer soil, physically engineer the light, essentially the entire growing environment to maximize the growth of this one cactus genus. And yeah, this is a strange company for a physical engineer. This was more of a hobby that I just grew. But I want to say that I think this is an interesting way to showcase the capacity that physical engineers can apply their knowledge. Feel free, though, if you are interested, to follow me on Instagram at lafafora_engineering. I'm always happy to have new people follow me. So, moving on to the final topic of our presentation is more personal for me, as this is where I'm going to get to talk about the research that I'm doing for my PhD. So this is more of a change of pace from what engineering physics is and where we can go with it and what the faculty does, blah, blah, blah. And it's more of a small, detailed example of what one physical engineer can do. So I'm actually going to show two different research points, and the one comes to the ethical development in nuclear engineering students. Moving on to the final topic of our presentation is more personal for me, as this is where I'm going to get to talk about the research that I'm doing for my PhD. So this is more of a change of pace from what engineering physics is and where we can go with it and what the faculty does, blah, blah, blah. And it's more of a small, detailed example of what one physical engineer can do. So I'm actually going to show two different research points, and the one is about engineering ethics with my supervisor, and the other one is the PhD research that I'm more focused on. But the reason why I want to show the ethics one is because I think it's unique that a physical engineer is doing this kind of research as well. So the first thing that we're going to look at when it comes to the ethical development in nuclear engineering students is that we were actually able to find that if we included a new pedagogical teaching tool, such as called inquiry learning, this component actually helped the students understand the socio-technological aspects of a nuclear energy system so much more that they were able to develop their ethical understanding far beyond what I would expect from a third-year student. What's important, though, especially from an accreditation standpoint, is that our students actually maintain and retain the nuclear engineering knowledge that we are teaching them. And would you believe it? They are. So in this one course, not only do the students still learn what they were supposed to have learned and have always learned, but now they're actually being given an opportunity to grow their ethical beliefs, to grow themselves as an engineer. Overall, though, in this research project, we actually had students highlight fundamental perspectives of nuclear engineers that we, as the educators, are actually we should be focusing on this to teach more effectively and allow the students themselves to become a more confident engineer. It's important to be a confident engineer when you go into the workforce. Now we can actually get into the bread and butter of my PhD, which is focusing on long-lived radionuclide migration. So before we get going, just a little bit of background. In Canada, anyway, we've had nuclear power reliably supplying electricity since the end of the 1950s and moving on into the early 60s. So for the last 60 to 70 years, Canada has just been reaping the benefits of nuclear power with no proper long-term plan for disposal. And Canada is not the only country to do it this way. This is how the world worked. So in my mind, I think the current method of disposal is more considered like an intermediate storage with no definite end date. And then actually I'm going to bring this up with this so that little red circle I just brought up, I think that's where the above ground waste storage is at Bruce, and you can just see it sitting right there, right on the edge of the water. Just nobody touches it. And it's like, well, that's sort of a waste, isn't it? It is. So Canada and a large proportion of the world have actually come to an understanding that a deep geologic repository will be the most effective solution for the proper and safe disposal of our nuclear fuel. So what this did was it actually led to the Canadian government creating the Nuclear Waste Management Organization, and this body was tasked with finding a suitable location for the DGR. And when they found this location, they had to actually construct it, transport all the fuel to it, fill the DGR when it's done, and then seal it all off. And then they need to actually continually observe it. So currently on this map, the final two locations that we have are number 5, which is Ignace, and that's in a crystalline rock formation, or number 21, which is South Bruce, and that's in the sedimentary rock formation. So when we consider the reality of how fast these elements actually move through the engineered barriers, through the natural barriers, coupled with the elements having half-lives of 200,000 plus years, there actually is a real possibility that these long-lived radioactive elements could migrate upwards to where humans live and pose a radiological threat. So right now, the DGR concept is an underground repository 500 meters below the surface in either the sedimentary or granite rock. They haven't decided the final location yet. Then we put our spent CANDU fuel bundles into these copper-coated used fuel canisters, which are then placed into a MX80 bentonite buffer box, which is then sealed into a shaft with a backfill. And then when the repository is actually full of all the nuclear waste, it's fully sealed. So the MX80 bentonite there and the sedimentary or crystalline host rocks, they act as the natural or engineered barriers in our DGR concept to retard the migration of radionuclides as much as necessary to have a valid safety analysis. So where do I come into play, though? And I actually do two things. I do both experimental work and computer simulation work. And actually, we've just been given a contract to understand and diffusion of long-lived radionuclides onto the exact same rocks that are used in both engineered and natural barriers of the DGR concept. So I'll be doing experiments on granite, I'll be doing experiments on MX80, on all the rocks that you would find in the real locations. So the radionuclides that I have worked with, though, are selenium, technetium, europium, and palladium. Our group actually just got a contract from the NWMO to start doing some uranium research as well. And I'm actually going to try and find a way to do some plutonium research, as if you didn't know, you can't work with that element here in Canada. So the way that I personally obtain information is by doing batch sorption experiments. So what that means is I take some solid, some liquid with the element in it, and I just see how much of the rock is actually capable of grabbing onto the elements and preventing them from moving further. It's like a sponge, it's absorbing them. So this work can be completed in an atmosphere for oxidized elements, but more importantly, to replicate the DGR, deep geologic repository conditions, they have to be in a glove box that has reduced conditions maintained chemically and atmospherically for long periods of time, which is actually quite difficult, but we can do it. Using the experimental data that I do collect, I actually am able to create models that quantify the capacity of the rock itself to absorb elements across large pH ranges and across wide ionic strength ranges. So this is necessary because we don't actually know the exact water conditions at the DGR depth. So we're actually trying to do it for any possible groundwater composition that could ever be expected. Moving forward, the simulation work that I do is actually in a completely different realm of the scientific world. on density functional theory and molecular dynamic simulations of these radionuclides. So before I hit the button anymore, up here in this top left GIF, you see a montmorillonite clay sheet, water bouncing, and then there actually is a single neptunium NPO2 plus cation right there. So what the DFT simulations allow me to do is to develop and model atomistic representations of radionuclides and their possible species from pure quantum physics. So I'm using Schrodinger's equation to do this. And this is what a physicist does. This is a theoretical physicist's job. Then what I do is I take these modeled molecules and I make a clay simulation like this one. And then I apply thermodynamic constraints. And what I do is when I apply the thermodynamic constraints, I then do molecular dynamic simulations. And the molecular dynamic simulations, upon completion, I can analyze them and determine theoretical diffusion coefficients for any radionuclide that might be in the DGR. So in the event of that neptunium NPO2 plus cation you saw, I got a diffusion coefficient of 1.19 times 10 to the negative 10 meters squared per second. So they're very, very slow. And this becomes a very powerful tool to me because when you consider real-life diffusion experiments, you could be waiting multiple years for a single value, or you could be waiting forever and never actually measure an outflow concentration. So you'll never actually get a result. But I can get you a result in just the same amount of time as I can get another result, and that's a key thing. In addition, what has actually been discovered is that diffusion rates from a diffusion experiment and diffusion rates from a sorption experiment do not correlate correctly. They don't line up. So this is a great simulation tool to be able to figure out why. And then would you believe it? I actually was the first place recipient in the doctoral research category at the Canadian Nuclear Society conference this year for this research. I couldn't believe it. I thought it was pretty cool. But anyway, ultimately, all the work that I am doing is going to be used by the NWO itself to determine possible concentrations of radionuclides that can reach the surface. And then when we consider the radioactive decay of these elements, we can quantify and compare to current safety regulations. Is the public safe? So keep in mind the amount of work being done to ensure that the DGR will work long into the future is immense. But anything can happen between now and 1 million years into the future. And that means that the amount of work being done to ensure that humans are safe in essentially any scenario is also immense. Like, I mean anything. They have considered ice ages and meteors hitting directly where the DGR is. Just the same. So basically, that's my whole presentation per se. And I'm actually very excited to have presented this today. And I hope you had a chance to enjoy it and you didn't doze off too much. But I would actually enjoy if anyone would like to reach out and ask me a question. By all means, feel free. Just send me an email. I've actually included a picture of my business card here at the bottom, and my email is on there as well. And so is my LinkedIn. Add me on LinkedIn. So if you want to, though, feel free to send me an email. Ask me about McMaster. Ask me about engineering physics. Ask me about you getting a career or getting a job in Canada. My own research, my cactus business, if you want to. I'd actually be happy to answer you and hopefully help you out with anything. So once again, though, thanks so much to Maria for the personal invitation. I'm really, really happy to have accepted it. The university for having this wonderful engineering event for you all this week. And finally, just thank you all. Thanks so much for watching the presentation. It meant a lot that you were all able to sit around for almost 40 minutes and listen to me talk. So I really hope that you take care, you have a great rest of your day, and that you have a great rest of your weeks as well, and that you get to enjoy the rest of this online academic week of engineering. All right, take care.